Random train test splits can fake your NDCG. Query group splits with LightGBM show whether your LTR model actually ranks unseen queries better. You'll learn how the pieces fit into a workflow that plans query grouped folds and reports held out NDCG. I'm Professor Pi, teaching search and IR with simple Python. Search evaluations often use random row splits because they're easy. The problem is subtle. If the same query ID appears in both train and test, a model can learn query-specific shortcuts and score well offline without actually generalizing. That mismatch shows up later when deployed ranking fails on new queries. Even though your offline numbers looked great, grouped splits stop that by keeping every query wholly inside one fold, so the metric actually measures how the model handles fresh queries. Put simply, instead of chopping rows at random, we partition by query ID. Picture 3 queries, each with several documents. If one query ends up in both train and test, you're effectively testing memorization. If each query stays in a single fold, you see how the model deals with unseen query text. The downside is higher variance when there are fewer unique queries per fold, so you do need to pick fold count thoughtfully. We'll walk a tiny pipeline that first makes leakage obvious, then fixes it with GroupKFold, and finally reevaluates with LightGBM's ranking objective. This isn't production code. It's a compact, reproducible demo you can scale up to your data. Quick note, this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. First, we construct the toy dataset so you can spot repeated query IDs and query-conditioned features. This snippet assembles a pandas data frame that mirrors a minimal learning-to-rank workload with repeated queries and engineered features. Query IDs repeat 4 times each, so you can easily spot whether any split will scatter the very same query across training and evaluation. The additional Q-code column is a deliberate stand-in for query-conditioned features that ranking models happily memorize, while ftitle and fbody supply per-document variation for later scoring. Seeing the printed dictionary of rows per query confirms the toy set is balanced, which avoids misdiagnosing leakage as a class imbalance artifact. Next, we simulate a careless row-wise split to show how overlap looks numerically and why that is dangerous. This example slices the data frame by taking the first 2 documents from every query, just like a careless row-wise split that ignores grouped relevance judgments. Because each query contributes items to both train IDX and test IDX, the shared list comes back with all 3 queries, and leak radio lands at 1.00, flagging total query overlap. The feature calls list isolates the signals we will feed to LightGBM later, so you can reuse it without rewriting downstream code. That printout proves any offline metric built on this partition will be contaminated by leakage before we do a single fit. Now we let a ranking model train on that leaky split so you can see how the metric is fooled. This code trains LightGBM's LGBMRanker with the lambda rank objective on the leaky split and scores it with scikit-learn's NDCG score. Because train DF still contains every query ID, the model can map Q-code directly to the relevance labels you already exposed. So the fitted booster predicts the held out documents almost perfectly, even though they represent 0 generalization. The scored data frame keeps predictions lined up with their true gains, so the group by lambda evaluates NDCG per query instead of smearing scores together. Watching naive NDCG hover near 1 underlines how seductive a leaky validation can be before you inspect the split. To prevent that, we build the group-aware fold inputs so the splitter knows query boundaries. This snippet wires up scikit-learn's GroupKFold inputs, so the splitter understands our query boundaries. By exporting the feature matrix X, relevance vector Y, and group array once, you avoid recomputing conversions each time a fold runs, which keeps later loops slim. The holdouts list shows exactly one query per fold, because GroupKFold guarantees whole group assignments rather than random rows. Seeing disjoint true tells you the stage is set for query-disjoint evaluation, so any remaining inflation must come from the model rather than sloppy indices. Finally, we run the grouped folds with LightGBM and report honest NDCG on unseen queries. This example reuses the GroupKFold object to train LightGBM with lambda rank on each pair of infold queries and evaluates the unseen query with scikit-learn's NDCG score. Because each fold holds out an entire query ID, the booster never sees that Q code during fit, so the reported mean score reflects true query-level generalization rather than memorized judgments. Rolling total NDCG, instead of storing per-fold metrics, keeps the loop compact while still tracking how many folds ran. The printed GroupKFold NDCG captures the leakage-free baseline you can trust, even though more folds would trade some training data for tighter variance. In a real project, you would map Q code to real query signals, use larger query counts, and increase fold count to balance variance. The toy pattern directly translates build grouped folds, avoid per-query leakage, and compute per-query NDCG averages as your primary metric. Recap: query group splits evaluate whether models generalize to new queries. Use them when your dataset contains repeated query IDs or query-conditioned features. Caveat: grouped folds reduce training data per fold and increase variance, so choose fold count with care. Next step: tune LightGBM's num leaves and learning rate while holding folds grouped to see how complexity and regularization change honest NDCG. If short, practical IR helps, subscribe and watch the IR videos.